Professor Garg directs the People AI Robotics Lab at the University of Toronto. He's a faculty member of the Vector Institute and a senior research scientist at NVIDIA. The research focuses on developing general-purpose embodied intelligence that is capable to learn from imprecise information, achieve human-level efficiency and flexibility. We're excited to have you here and listen to your talk on paving the path to robot autonomy with simulation.
Thank you very much. Thank you for the patience of all the in-person audience to accommodate all of the people who are remote. I am not, unfortunately, at ICRA, but it feels that the workshop has been a wonderful turnout of talks and posters, and overall the conference has been wonderful. So I'm having real FOMO here. For everyone else who joined us now, I'm Animesh. I'm currently a faculty at U of T, and I split my time between NVIDIA. And most of the things that I work on are thinking about how we can build learning-based robot manipulators, and more recently, learning-based robot mobile manipulators. So what I'm going to talk about today is the idea of or the problems that I'm working on in enabling robot learning at scale. So let's get started with the big picture idea, right? So let's start thinking about learning, particularly as a beginning problem. Learning of late in the last few years, you could argue, has been powered by three main components: large-scale structured models, data, and compute. And this has essentially resulted in increasingly high performance, whether it's in computer vision or language. Now, if you really look at these ingredients of modern machine learning, models, data, and deployment, they don't really work for robotics in a sense, right? That we don't have the same scale of models. We definitely don't have the same scale of data sets. And we are really not using cloud computing for either training or inference at the same scale as, let's say, people in transformers for language models are using. Now, one could argue, how do we build robot solutions? One solution mechanism can be, well, we build in domain expertise, one problem, one solution. A lot of these solutions would be structured, where we build in domain knowledge. The other aspect of it can be, well, let's go all data on it, just add data, and hopefully an end-to-end mechanism would work. Well, practically, neither of them are sufficient, right? You could argue that neither achieves generality at scale. On one hand, you would have basically the interplay of performance versus flexibility. On the other hand, assuming the data-only approach were to work, where is this data going to come from, and how is this going to generalize? So in principle, a lot of the work that I do talks about thinking of two particular technical problems. One, the structure, what sort of structures, inductive biases, and priors do you need for decision making? And the other one is, how can we use and collect large-scale data for robotics? And for today, this talk, I'm going to focus primarily on the aspect of data. If we were to think about data in robotics and sorts of problems we want to do with the data, whether it's planning, perception, control, it appears that there are way too many sub-problems, if you think about, to create data sets. We can talk about creating data sets for grasping, then what about kitting? If kitting is done, then what about machine tending? If machine tending is done, what about packaging, and so on and so forth. It seems that robotics is not at the same level as people have reduced vision and language problems to create these large-scale data sets. And that is precisely where my argument comes in, where I argue that simulation is the data factory for robotics. Simulation is the primary mechanism with which we can scale data sets in robotics, very much in the same way folks in vision and language were able to rely on web data, even though web data was not always what you would call realistic data collected in the wild, but it was a very good proxy that researchers were able to clean up and figure out how to use it. In the same way, I would argue that we need, despite all of its flaws, simulation provides us scalable procedural data that we should figure out how to use in building or in our quest to build practical systems. So now what I'm going to describe today is 3 particular research ideas that we have been working on. The first one starts with talking about, if we are going to use simulation, how are we going to go to real robots? One solution can be through large-scale randomization. After that, we'll talk about, assuming randomization is not always possible, can we do better interactive estimation? And finally, I'll talk about why we should really think about robotics as a large-scale systems problem and focus on building simulation systems as systems engineering problems that would allow us to bridge this gap in a more engineering perspective. So let's get started with randomization as a problem, right? So randomization as a problem has been studied in a number of domains and has actually found quite a lot of success, I would argue, in many applications in robotics, whether it's perception only, perception to control, or even a variety of these generative models that were used for transfer learning. I started doing sim to real transfer back when RL was not as popular in 2016. We were not really thinking about visual transfer. So we started creating these simple simulators, which would allow us to build, let's say, simulations of very simple gauze, which is a 2D fabric, and we need to cut a pattern along it. This is a task in surgical subtask autonomy. So what we did was we created very simple simulators. The simulator itself is not some finite element model. It's actually just a single Python file, surprisingly. And we were able to train an RL policy on that simple simulator and put it on the real world robot. And surprisingly, it worked. That was my first foray in putting sim to real. At the time, I was very surprised that it did anything at all, given the simplicity of the simulator, which piqued this interest in me that what would it take, or when would this transfer work? When would this transfer not work? How much simulation or how much transfer, how correct does the simulation need to be? And how much randomization would we need for any of this model to work? So cut to sort of 2021, we started working on slightly harder problem of in-hand manipulation. And this time around, the problem was that the robot is actually not with us. We don't actually have access to the robot. The robot is remotely operated. It is available as a service. This was a challenge run by folks at MPI, which was called the Real Robot Challenge, where you had access to the system purely through an API, but not the real robot. So you cannot really tune it. You can only use the robot in limited amount of capacity. So then what we said was, okay, how do we train such a model in that case? People had shown that you could do sim to real training for a shadow hand. OpenAI had done that in 2018, 2019, but that process was very compute intensive to a point where it was not really replicable. Replicable, at least not in academia in a sense. So with a combination of fast simulation, I would say courtesy of Isaac Jim at NVIDIA, we started building RL-based pipelines for training an in-hand simulation model. In this case, because we were not using explicit poses, we started using the ability to track key points as state representations for objects in hand. And we were able to train essentially an RL policy that would be goal conditioned. So you can grab the cube and put it in arbitrary goal configuration without coding in any strategies. So we are not coding in particular strategies of gating or finger manipulation. And all of this was actually done purely on a desktop in about 1 day of training, which was basically, again, the fact that simulators were running fast enough that we could train an online on-policy RL algorithm, in this case, a PPO, to be able to achieve that. And we were able to also show that with sufficient amount of domain randomization, with correctly chosen parameters in randomization, we were able to transfer this policy that was succeeding 90+% in simulation directly to a robot. And during that evaluation, we found that roughly the policy would work 1 out of 6 times, which was surprisingly good, right? In a sense that this was supposed to be a hard task. We did not have access to real robots, so we were not what you would say overfitting to our real robot. We were just using our simulator. We are allowed to do whatever we want in our simulator as long as we can ship the policy off to work on the real robot, which I thought was very interesting and successful in a sense that practically this is the paradigm we want to be in, where we want to essentially just deploy the policy on a robot that we don't have direct control over. This idea of randomization was not just limited to manipulation, by the way. Another problem of interest where we thought that simulation would be very useful, but simulation may not be correct, was legged locomotion. So we also worked on a number of problems of building legged locomotion strategies with gate selection. So we basically say that low-level gates are pre-programmed with optimal controllers, and then the high-level controller, which is a learning-based controller, is selecting which gate to pick. And this high-level controller is essentially learned purely in simulation. And this is the training setup where you can put the robot on some treadmill and ask it to do interesting things. For example, moving on one part of the ground is moving while the other part of the ground is not moving, or the ground may actually be moving with variable speeds rather than the fixed speed. And what you see in the inset is basically the output of the high-level policy, which is switching these gates. Again, what we found was we were able to put this policy trained purely in simulation directly on the real robot. This time around, we were not doing extreme domain randomization. In fact, we were surprised that this worked, and this worked as well as it did. And it worked on a variety of other use cases where, for example, we didn't simulate exact ground friction. We just simulated the fact that a robot needs to be able to walk on frictionless surfaces. So this was an example where, again, I was actually surprised that how little we needed to do to go to the real robot. Next, we actually started thinking maybe it's working because it's purely an optimal controller at the lower level. So because of all of the robustness is coming through the optimal controller, the high level thing is just selecting policy. So we said that, okay, we need to pick a better action space and train end-to-end RL policies this time around. And what we did was we took away the whole gating process. We said that this time around, the action space is a centroidal action space. So we are going to learn this walking process purely with RL this time around. And the low-level thing would be just a QP solver, but only to compute viable ground reaction forces. And something similar and surprising happened yet again. This time around, we were able to, again, train purely in simulation and take that policy and put it on the real robot yet again. So in two different domains, one where we used very heavy domain randomization, and in the other one where we were not using a lot of domain randomization, we were able to train a policy that transferred to the real robot. So then the question that we were asking ourselves is, a lot of papers have talked about this idea that we need a lot of randomization, and well, more often than not, randomization is all we need. And we were now questioning that assumption. In fact, there was one myth on one side that sim to real is very hard and it will never work. Simulation is never going to match reality. The other one was, because that's true, randomization is always necessary and you have to do this in many ways, and so on and so forth. So we set out to actually just evaluate this question objectively. Like, is this actually true? So the first thing we looked at is, what is the process of doing this? If I was to build a simulator, I would look at my real system. I would say, what are the dynamics parameters? I will match them in my simulator and then hope that sim to real works. And then if the real policy doesn't work, then I will update my parameters and then carry on with the loop. Now, when we do randomization, we are hoping to create robust policies. If there is failure, you randomize more. That is like the usual algorithmic approach that the designer would take. Now, the question is randomization necessary? Some of the results you might see showed that sometimes it is, and sometimes it is not. So for example, if randomization is necessary, then the other question could be, is it sufficient? How much randomization is necessary? We found that even though we were randomizing it for walking, then if you change the state space, or if you change the feedback, then the policy starts to fail very quickly. Similarly, if the low-level policy controllers on the real robot are not tuned properly, irrespective of how much randomization you did, it would not work. So that left us with this argument that perhaps that's not true, that randomization is just a panacea, but perhaps design choices matter. So a practical thing to do might be, well, randomize nothing, and then when failure, analyze data, and then design issues to randomize specific parameters. So you want to do randomization, and it only matters in certain parameters, not everywhere and all the time. So the takeaway from this line of work, which was published last year at ICRA, was dynamics randomization is a very good idea. However, doing more of it can result in suboptimal policies. We can avoid heavy dynamics randomization if we understand the system fairly well, and should only be used if we understand the domain. If we randomize arbitrary parameters, it's not necessary that we'll always get robustness in transfer learning. So that was something that was, I would argue, counter to what has been the popular belief in machine learning and reinforcement learning for randomization. Now, randomization may or may not always be possible, particularly when either simulation is slow or data collection is harder. One example of that was actually cutting. Cutting is something that is very useful as a process in a number of manipulation tasks. However, so far it has been very hard to simulate cutting because of the process of cutting is fairly slow and involved. So this was a paper that we worked on last year at RSS, where we were able to simulate deformable object cutting, and we were able to make that process differentiable in simulation. So we use a detailed model of contact mechanics, which allows us to achieve realistic prediction of knife forces while maintaining the differentiability of this process. So this, I think I can skip this in the interest of time, but we used data that was collected by others on real robots for cutting to evaluate if our simulator was indeed doing the right thing from a perspective of real cutting. So this was equivalent to calibrating the simulator parameters to a realistic setting. And because our process is differentiable, the simulation process is differentiable, we were able to simulate, we were able to match the cutting forces, and in the process derive the correct parameters for cutting. Then we can now use this framework to create, let's say, optimal control-based cutting strategies where we performed constraint optimization, and we discovered that in this process, the gate of going back and forth for cutting emerges rather than to minimize the forces rather than cutting a straight through open loop. And now we were able to put this process directly on the real robot. In some cases, this process was by adapting the knife and the object properties. And using that, we were able to create these continuous cuts in real systems. So again, the takeaway in this part of the talk should be really that simulation of phenomenon that are harder allows us to learn new kinds of tasks, which would be very hard directly on the real robot. However, not everything would be equally fast. In that case, online parameter estimation or Bayesian parameter estimation is going to be very useful for calibrating the simulator to the real world. Finally, I do want to talk to you about all of these simulators, as you saw, are special purpose simulators built for particular use cases. But as robot learning and machine learning researchers, often the limitation of using these frameworks is the onboarding, right? A student will spend 6 months building the simulator and it may or may not work. That process both slows down research and slows down the cycle time of us evaluating this on the real robot. So on that effort, we have been building what we call ICRA at NVIDIA, which is built for ease of use of simulators. We started using ICRA to interact with real-world articulated objects as a use case, particularly for large-scale articulated objects like drawers, cabinets, and cupboards. So to generalize this, we created large-scale procedural kitchens with many object models. This is something that can procedurally be done. And we created an abstraction for using the framework that enables what you would call easy interaction and definition of the task. You can define a world, and the world will contain two kinds of objects. One is a robot, which is actuated, and everything else, which is unactuated, is part of the scene. And then the agent can control the robot at different levels of temporal abstraction, at low level 1000 Hertz control, or at high level planning level control. And again, each layer of control can interface with a different layer of observations depending on the choice of abstraction of actions. And RL, in a sense, can only work with one layer of control abstractions. This sort of abstraction makes it easy to interact with these complex simulators without worrying about low-level physics, low-level scene definition, despite giving you, as the user, the power to define custom scenes. Skipping this. So now what we were interested in is to use this framework for building a goal conditioned reactive controller. So assume that some high-level model is giving you what needs to be done. So let's say if I want to open the oven, someone can give me a sequence of key points for the oven handle, and I want to be able to solve this for this particular oven handle on the fly using optimal control or a policy. So in this case, we want to show this that this can actually be done in the loop in a realistic setting. We did not assume access to privileged information. So we use perception in the simulation. We segment the input images, and then we create keyframe generator only for the object points of interest on the object. In this case, the point of grasping. And then we can use whole body controllers with real-time collision avoidance to create a plan such that the robot can come up with a trajectory that will result in the oven following the required keyframes or the set of keyframes. So we are defining the reference only in terms of key points on the object. And what we are showing you here is, in this case, we did not need training. The training is needed for high-level goal generator. However, for the robot, we are only using an online whole body controller. All of this is trained in simulation, in a sense, and evaluated in simulation. But interestingly, can also be put directly on the real robot. So this time around, we do not assume access to 3D models of objects or shelves or doors. We are performing real-time perception on the system, and this is in collaboration with ETH Zurich, Mark Rutter's lab. And we were also able to show that because we are using real-time perception, you can actually do dynamic collision avoidance, which basically is provided to you for free because you're solving an optimal control problem online. So just to put this back all together, I truly believe that simulation is required for robot learning. However, we need to think about when we need robustness through simulation randomization. When can we do algorithmic system ID? And finally, all of these frameworks need to be put together along with perception to build better simulation systems so that we can do scalable learning. Thank you very much, and I would be happy to take questions, and thanks a lot for the privilege of your time.